This week's lab is about earthquakes. In the first part of the lab, we're going to be using seismographs, which provide a record of the intensity of shaking, ground shaking at a given location during the passage of seismic waves. We're going to be using that record provided by seismographs to determine how far away a given station location is from the epicenter based on the difference in arrival times between the P waves, which are faster, and the S waves, which are slower. Because the P waves travel at faster velocities, they're going to arrive at the seismograph first and be recorded first. Then sometime later, the slower S waves are going to arrive. That lag time between the P and the S waves is a function of how far the given station is from the earthquake's epicenter. Now, each given station provides a distance from the epicenter, but not a direction. You're getting distance from the difference in arrival times between the fast P and the slower S waves, but you don't necessarily know the direction that the seismic waves are coming from. As a result, you have to use distances determined from 3 or more seismographs to triangulate the epicenter. And the way we do that is we basically go to a map. We've got distances for 3 different stations. Draw a circle around each station that has a radius equal to that station's distance from the epicenter. And if we do our measurements carefully, those 3 circles will intersect at a single point. That point is the epicenter. From seismographs, we also determine the Richter magnitude of the earthquake. Richter magnitude is based on the amplitude of seismic waves at a given distance from the epicenter. We already know the distance of each station to the epicenter based on the difference in arrival times of the P and S waves. We'll then measure the amplitude of seismic waves on that seismograph to determine the Richter magnitude. And the Richter scale accounts for decreasing amplitude with increasing distance of that station from the earthquake's epicenter. This seismograph shows P, S, and surface waves generated by the 2001 Nisqually earthquake, which had an epicenter near Olympia in western Washington. This seismograph was recorded all the way in Oklahoma by the Oklahoma Geological Survey. We're talking about several thousand kilometers from the earthquake's epicenter. Yet seismographs are sensitive enough to pick up the ground shaking, even if it's too small for people to actually feel. Again, our P waves are fastest, so P waves get there first. So here are our P waves with their faster seismic velocities. Next set of waves to show up are the S waves. S stands for secondary, slightly slower velocities. These are the S waves. Then finally, the last group of seismic waves to register on the seismograph are the surface waves. Waves that travel along Earth's surface, they are the slowest of the different types of seismic waves. And they also have the largest amplitudes. So for the purposes of determining the distance of this station from the earthquake's epicenter, we need to look at the difference in arrival times between the fast P waves and the slower S waves. So we find when P waves first start being recorded on the seismograph. Note the time. Find when the S waves first start being recorded on the seismograph. Note the time. We find, in this example, the difference in arrival times between the P and S waves is about 4.5 minutes. We can then use a seismic wave velocity graph to relate that difference in arrival times between the fast P and the slow S waves back to a distance of that station from the epicenter. So the x-axis, difference in arrival times between our P and S waves, as measured from the seismograph. The y-axis is the distance to the epicenter that corresponds to that difference in arrival times. For example, if you find that the P and S waves start about 60 seconds apart, 60 seconds corresponds to a distance of about 600 kilometers for that station from the earthquake epicenter. In the case of the Nisqually earthquake, difference in arrival time was 4.5 minutes. Well, 1 minute, 600 kilometers. So we have a distance from the Oklahoma station to the epicenter of about 2,700 kilometers. Now again, each station gives only a distance of that station to the epicenter, but not the direction. So each station defines a circle of possible locations where the radius equals distance of that station to the epicenter. So take a compass, this kind of compass, use your scale bar to measure out the distance that you determined from the difference in arrival times, and then draw that distance on the map as a circle centered on that particular station. So here we've drawn a radius, a circle with a radius of 2,700 kilometers centered on the Oklahoma seismograph station that recorded the Nisqually earthquake. The epicenter could have been anywhere along that circle. As a result, we need at least 3 stations to triangulate the epicenter. Three stations, each has its own unique distance. Own unique distance from the epicenter, from the difference in arrival times between the P and the S waves. Defining a circle of possible locations for the epicenter. 3 circles intersect at a single point. That point is the earthquake's epicenter. So here's the sample seismograph that you have in the first page of your lab packet. Here we see on each of the seismographs you're working with, the time that P waves first start being recorded is set to time 0, which is of course sometime after the earthquake, depending on how long it took P waves to reach the station. It's a function of how far that station is from the epicenter. S waves arrive sometime afterwards. Here's where the S waves first start arriving. That difference in arrival times for this sample is 36 seconds. We'll use that difference in arrival times to determine a distance of that station to the earthquake's epicenter. To determine the magnitude of the earthquake, the Richter magnitude, we also need the amplitude of seismic waves. Amplitude is defined as the maximum deviation from a horizontal line. So you're not measuring total vertical difference, but rather difference from 0, difference above or below 0. Maximum wave amplitude for this example is about 185 millimeters. So in the example, we found the P difference in arrival times between the P and the S waves was 36 seconds. We find that that 36 seconds corresponds to a distance to the epicenter of about 365 kilometers. Now this is the Richter scale, which you also have in your lab packet. You can see the Richter scale relates amplitude to distance from the epicenter to find the Richter magnitude. In so doing, the Richter scale accounts for the fact that, all other factors being equal, the amplitude of seismic waves being registered on a seismograph will decrease with distance of that seismograph from the earthquake's epicenter. In the sample seismograph, we found that a station that was 365 kilometers from the epicenter, with a difference in arrival times between the P and the S waves of about 36 seconds, produced an amplitude of ground shaking of about 185 millimeters. Draw a straight line between those 2 points. See where they cross the third axis, the middle axis, which is the Richter scale. We find a magnitude for that earthquake of 6.4. 6.3 to 6.4, something like that. Now you have 3 different seismographs to work with. Each one is at a different distance from the epicenter, so it has a different amplitude of shaking. But remember that the Richter scale accounts for the difference in amplitude with distance, changing distance from the epicenter. Each of your 3 seismographs should give you approximately the same Richter magnitude to within a tenth or so. There can be small differences in amplitude that are not due to distance from the epicenter, but instead due to site-specific geologic conditions. In particular, how the seismic wave amplitude is affected by passage through different types of rocks and sediments with different densities. So in the second part of the lab, we're going to be looking at how the amplitude of ground shaking and the intensity of damage from the earthquake varies as a function not only of how strong the earthquake was and how close a given location is to the epicenter, but also what types of geologic materials are found at that particular location. In other words, the amplitude of shaking that you see at any given site is affected by the types of geologic materials those seismic waves are passing through. When seismic waves are passing through dense rocks, such as igneous or metamorphic rocks, they travel at faster velocities. As a result, they have lower amplitudes. But as density decreases, seismic waves passing through that material slow down, and as a result, their amplitudes increase. So geologic materials that are dense, such as igneous rocks and well-consolidated compact sedimentary rocks, waves are relatively fast. Then they get slower in materials with lower densities. As a result, their amplitudes are increasing. As velocity of the seismic waves decreases. So if you build your house, let's say, on soft, unconsolidated sediments, especially material that's water saturated, you're going to experience a larger amplitude of shaking for a given magnitude and a given distance from the epicenter. If your house is built on solid bedrock, you're going to experience a lower amplitude of shaking, even at the same distance from the epicenter. As a result, we'd expect more damage, more intensity at locations built in softer material with slower velocities and higher amplitudes, and less damage and intensity at sites built on dense solid bedrock with faster seismic wave velocities and lower amplitudes of shaking. So in the lab, you're working with the 1989 Bay Area earthquake that occurred during the World Series. Some of you may be old enough to remember this event. You've been given a list of towns with observations of the damage and intensity of shaking caused by that earthquake. For each location, you're going to assign an intensity value using the Mercalli intensity scale. Now, this is a somewhat qualitative exercise. So half of the locations have been done for you. You'll need to assign intensities for the other locations. And as long as you're assigning higher values to locations with more damage and lower values to locations with less damage, you'll get the right pattern. You're going to go to the map, plot the intensity value for each location, and contour the data as a way to visualize the spatial pattern of intensity. This is an intensity map not for the 1989 earthquake, but for the 1906 earthquake. Its epicenter was approximately there. Now, you would generally expect intensity to decrease with distance from the epicenter. However, intensity can be locally higher where your seismic waves are amplified by soft geologic materials. For example, we see the highest intensity not at the epicenter, but near Santa Rosa, telling us that waves, seismic waves, are passing through softer materials in that area. They're slowing down, and their amplitude is increasing as a result. So when you make your intensity map for the 1989 earthquake, what you're going to find is that there are two areas of maximum intensity. One near the epicenter, as to be expected, and the other where waves were amplified by soft geologic materials.